In this demo, we'll start off our data science lifecycle by doing some exploratory analysis on top of our did not attend dataset using Oracle Analytics Cloud. As a citizen data scientist, I want to be able to quickly understand the data I'm working with and make any necessary changes in terms of data cleansing, transformation, or feature engineering before testing out any ML techniques. Before we take a look at the visualizations, I'm going to switch to Oracle Analytics Cloud Dataset Editor, which allows me to assess the quality of my data, make transformations, but also create new features if required. Our did not attend or DNA dataset contains demographic, health, and behavioural information around patients and whether or not there have been a show or a no-show to previous booked appointments. And I can go ahead and assess the data quality using the data quality insights at the top. I can see the distribution of my data. If there were any missing values, I'd be alerted at the top to say that there were, 5%, 10% missing values. I can start transforming my data by right-clicking on a column, depending on whether it is a categorical or numerical column. I'll get slightly different data manipulation techniques. And I can, for example, edit the column. So with our travel time, maybe I want to reduce it down to 2 decimal points. So I can search for different inbuilt functions that we have on the right-hand side. For example, rounding. And I can either simply drag and drop the calculation, or if I kind of know the syntax already, which is in the documentation here, I can automatically add that into the expression editor. So I can round my travel time to 2 decimal places, validate it, and then you should see the changes happen below. And once again, I'm just going to add that step. If we have a categorical column, you can do a similar thing. You can click on the menu option and you get various different transformations that you can do. And right at the bottom, if you want to, you can create your own column from scratch as well. So now that we've gone through the dataset editor, let's jump back into the dashboard. So we can see our dataset consists of just over 100,000 patients who have previously booked appointments with us. We can see how many of them have attended those appointments and how many have been missed. And we can visualize that as a distribution. So we have a rough 70-30 split. And we can start slicing and dicing that data by different attributes. So for example, how does the travel time affect people's attendance? And here we can see, using this box plot, the patients who have missed appointments typically have a higher travel time to the surgeries. On the right hand side, we can look at the distribution of patients who show up to appointments based on their history of whether or not they've shown up. And we can see here people who have previously missed appointments have a much higher percentage of missing the current appointment. And down below we can look at things like deprivation area. So people in a more deprived area are more likely to miss appointments than people in a less deprived area. And also we can see if there's any trends looking at the age of the patients. However, looking at this, it looks like it's pretty consistent that around 25 to 30% of patients miss their appointments. However, in the later ages, it does slightly tend to drop off and you get slightly less percentage of those patients missing those appointments. So it's always important to explore your data and understand the data you're working with before building any sort of machine learning model. In this demo, we'll take a look at how, as a citizen data scientist, I can build, train and evaluate a machine learning model without writing a single line of code using Oracle Analytics Cloud. Oracle Analytics Cloud is embedded with machine learning capabilities that allow citizen data scientists to quickly prototype, build and measure the business value of machine learning models before having a data scientist build something more robust. Let's see how we can quickly train a machine learning model on top of our did not attend dataset to predict no-shows. First, we're going to go ahead and create a data flow, which is a lightweight ETL tool that allows us to extract, transform and load data, but also build up our machine learning workflows. So first I'll be prompted to select my dataset. So I'm going to go ahead and select my training dataset and add that to the workflow. Now on the left hand side we have various nodes that allow us to transform our data, but we're interested in our machine learning ones down at the bottom. And I'm going to go ahead and drag and drop a train binary classifier node on top of my dataset. Now the reason it's a classification problem, because we want to classify our patients into a show or a no-show. So into distinct buckets, and it's a binary classification because there are only 2 outcomes, a show or a no-show. So once we've done that, we're going to be asked to select our algorithm. Just for this, we're going to go ahead and pick the logistic regression model. And the first thing we need to do is select our target column, or the column we want to make a prediction on. So I can go ahead, scroll to the bottom to did not attend. So 1 represents that they will be a no-show, and 0 represents there will be someone who turns up to their appointment. So the one we're interested in, or the positive class, is set to 1. And there's various other parameters you can play around with and adjust, but I'm going to leave them as default. I can then click on the Save Model node and let's give it a name. So let's call it ML DNA risk. And finally, I can save my data flow before running it. So let's give it a name and click on OK. So what it will do is load in my training data set. It will go ahead and build me my logistic regression classification model, and then it will save that model output into our model catalog, which we can then go ahead and evaluate the performance. Perfect. So that took just under a minute to train. I think the training data set was 100,000 records. But once that's done, I can head back to the home page, click on a menu, visit our machine learning model catalog. I can right click on my model, do inspect, head over to quality metrics, and it'll give me some information such as model accuracy, precision, recall, the confusion matrices. And essentially we can evaluate this model to see, you know what, is it able to make predictions depending on our task? And if it is, maybe we test this out with the business and get their buy-in. And from that, we can then pass in all our knowledge to a data scientist who can build a bit more of a robust model on possibly a wider data set. In this demo, we'll take a look at how we can build, train, evaluate, and explain our did not attend machine learning model, and also make predictions on which patients are likely to be a show or no-show for future appointments. Using the OCI Data Science Service, which is based on open source Python and Jupyter Notebooks, I can step through and address the end-to-end data science lifecycle. Now, I could utilize the common open source Python libraries. However, I'm going to utilize a couple Python libraries, namely ADS and AutoMLX, which have been developed by Oracle to help speed up the typical tasks within the data science lifecycle. So let's step through this notebook together. So first thing we want to do is read in our data set. And you can see we have just over 100,000 records of previous patient interactions with the practice. And for each patient, we can see their demographic information, some health metrics, and also some previous behavioural patterns as well. And the column we're interested in predicting is did not attend. So 0 is that they were a show, and 1 is that they were a no-show. Once we have our data set, we can start doing some exploratory analysis using the ADS library. And in one line of code, it will automatically create you the best visualization it thinks represents your data. And all you have to do is pass in the columns of interest. So here I can pass in a categorical value and it'll automatically create me a bar chart. And if I scroll down, I can pass it a categorical and continuous value. So did not attend by travel time, and it'll automatically create me a violin plot. And then down below, I can pass in two continuous variables and it will create me a Gaussian heat map. Once we've done our exploratory analysis, I can then start doing some data preparation, and I'm going to split my data set into a training set and a test set, where I'm going to train on 90% of our data and test it on the remaining 10%. And once I've split my data, I can then start doing and building my machine learning model. And I'm going to utilize the Oracle AutoML package, where all I have to do is pass in my data set and the list of algorithms I'm interested in. And Oracle AutoML will automatically select the best algorithm. It will automatically do adaptive sampling and feature selection on my dataset, and also do some hyperparameter tuning on my model. And it will do this all behind the scenes for me and output me with a leaderboard with the best models. So here I've selected my different algorithms. I've set up an AutoML pipeline, and then I can go ahead and train my model, passing in my training data. And you can see it'll go ahead and run all the different experiments and output me with the best one. So here we can see my optimization metric was accuracy, the number of selected features that were chosen, the best algorithm, which was an XGBoost classifier, and also the set of selected hyperparameters. And down below it'll also show me what came in second place, third place, fourth place, and so on. And the good thing is I can start visualizing the different trials I went through. So in terms of algorithm selection, you can see my XGBoost classifier came in first place, followed by the rest. It did the adaptive sampling to find the smallest subset of data without compromising accuracy. It will do the feature selection to find the most optimal subset of features without compromising my accuracy. Here it chose 8 features out of the total of 18, I believe. It did the hyperparameter tuning, so tweaking those parameters to find the best combinations, and you can see it actually went through maybe 80 or if not 90 different iterations to find the best combination of parameters for the model. Now once a model's trained, we want to evaluate it, and there are loads of different evaluation metrics when it comes to machine learning models. And to kind of calculate all of them and visualize and display those metrics, it does take a lot of code. But once again, using the ADS library in a few lines of code, we can pass it the model, training data and test data, and it'll automatically calculate us things such as accuracy, precision, recall, F1 score. But also, we can get it to display it visually in different charts. So we can look at our precision and recall, ROC, lift and gain charts, but also look at our confusion matrices to see how well did our model perform. And once we've done that and we're happy with the model, we can then go ahead and make predictions for each individual patient in our test data set. If I scroll across, we can go ahead and get a prediction. So there'll be a show or no show, and also a confidence level to say how confident the machine was in its prediction. Now it's all well and good knowing what will happen. So this person will be a show or a no show, but it's more important for the business to understand why certain things will happen in order for them to take preventative action. And using the AutoML-X library, we are able to do both global and local explainability, where global explanation explains how the model performs overall, and local explainability focuses on individual predictions or patients. So at a global level, we can see the different columns that influence the prediction, so whether or not there'll be a show or no show. So we can see the biggest influencer was if they had a history of no-shows, followed by their phone number in our records, travel time, and whether or not they're from a deprived area. And we can see how each one of these individual features also plays a role in influencing the prediction using partial dependence plots. So once again, it is only 1 or 2 lines of code, and we can see here for history of no-shows, if they do have a history, there is a high probability of them being a no-show. And similar with travel time. As the travel time of the patient increases, especially after half an hour, we can see the probability of them being a no-show starts to increase and increase. And like I said, we can look at this at a local level as well. So for each individual patient, we can understand why that the model has made that prediction. And first we'll look at a patient who's been predicted to show up, and we can see their travel time is only 20 minutes. They haven't got a history of no-shows. We've got their phone number in the records, and so on. However, on the other side of things, if we look at a patient who's been predicted to be a no-show, we can view the explainability rules to see that they do have a history of no-shows, they're from a more deprived area, their travel time is nearly 2 hours, and their age is 26 years old. So once we've kind of gone through those steps and built, trained, evaluated and explained our model, we can then package it up into a model artifact, which contains our model, the Conda environment, and different other metadata you want to include, you can do as well. And we can take that artifact and save it to our central model catalog for other data scientists to go ahead and access and make predictions on top of it. So once it's in the catalog, I can go ahead and make predictions for the patients for the upcoming week. So what I'm going to do is read in my new data set, which has 250 appointments that I have booked for the upcoming week. I can load in the model that we just trained that's stored in our catalog, and then I can start making predictions against that model. And for those 250 upcoming appointments, for each patient, we can go ahead and make a prediction to say whether or not there'll be a show or no show, along with confidence levels. And also we can run that explainability to understand why that's going to happen. So once again, if I scroll to the end, we'll get our predictions, our confidence, and those top 5 explainability rules to say why someone will be a show versus a no-show. And I can finally take all those results and save it back to the autonomous data warehouse, where I can then start visualizing the results using Oracle Analytics Cloud. In this demo, we're going to take a look at how we can use Oracle Analytics Cloud to visualize the output of our predictions from our did not attend risk model. So we can see the 250 appointments we had in the upcoming week for our different patients, and we can see the results of the predictions at the top. So 219 were predicted to be a show and 31 were predicted to be a no-show. And because this was historical data, we can also compare it against the actuals that really did occur for that week. So looking at the distribution, we can see, 87, if not 88% of our appointments were a show and 12% were a no-show. We can then start looking at the distribution of the confidence level of each of those predictions for both patients who were predicted to be a no-show versus a show. And we can see, looking at this box plot, that people who were predicted to be a show, the model was a lot more confident than it was in predicting no-shows. And down below we can get some of the results of the patients who were predicted to be a no-show. So for example, this patient over here, they were predicted to be a no-show, and we can see the confidence level of the model, but also the top 5 explainability rules of why the model made its prediction. And we can see the first rule was that they have a history of no-shows. We can see the travel time to the surgery was around 83 minutes, so about an hour and 20. And maybe this person had an appointment at 8 o'clock in the morning, and to travel in for an hour and a half nearly to their appointment might be a bit difficult, hence they might miss the appointment. So maybe here we want to take some sort of preventative action, reach out to this patient and essentially have a conversation to say, if we were able to move your appointment to 10 o'clock in the morning, would that give you enough time to travel to your appointment and hence show up? So essentially the practice manager can kind of go through this list and identify people who will be a no-show and see if they can set reminders for those patients or take some sort of preventative action to increase the probability of them turning up to the appointment. In this demo, we're going to have a quick look at a very important stage of the data science lifecycle around ML ops, and more specifically ML monitoring. Machine learning models don't perform optimally forever, and over time their performance starts to degrade for various reasons. Within the OCI Data Science Service, Oracle have developed a set of Python libraries to help monitor and track both model and data drift metrics over time, to help give data scientists an indication to when they need to retrain their machine learning models. In this notebook, we'll select the metrics we are interested in, and the SDK will calculate our baseline metrics based on our training test data set we selected, and then for each week we make a batch prediction on our new data, where we can then have this script run to then recalculate our new metrics and compare how they've moved from our baseline. Now, I'm not going to go through the whole notebook, as Oracle's Python library handles all the calculations, but I'll just go through some of the metrics we're having a look at in this demo, and we'll take a look at the outputs within Oracle Analytics Cloud. So I'm just going to focus on the imports, just so you can see some of the metrics we're using in this demo. And by no means is this the full list, but just what we're using for this demo. So we've got things like data quality metrics, where we can look at for a selected feature how the count, min, mean, standard deviation is changing, data integrity checks to see, the row count, distinct counts, duplicate counts, and also those model metrics. So in our case, we're focusing on a classification problem, but we have similar metrics for regression as well, looking around accuracy, recall, precision, log loss, ROC, AUC, and so on. We've got data drift detection metrics. So for example, looking at chi-squared, population stability index, Jensen-Shannon, Kullback-Leibler. So seeing how for each individual feature, how they're kind of drifting week in, week out from your baseline data set. Now, what I want to do is actually just jump straight into Oracle Analytics Cloud to show you a dashboard of some of these metrics visualized. So at the top, we can see some of those model metrics, such as our baseline and current model accuracy, our precision, our recall, and how that's changing from when we trained our model to the current point in time. And the good thing is you can set up a few alerts. So if something drops below a certain threshold, it can be set to red, or if it's starting to drop, you can set it to amber. We can go ahead and see how that model accuracy is changing week in, week out with our batch predictions. For each individual column or feature, we can start looking at those data quality metrics. How is the mean value changing? Is it increasing? Is it decreasing? What's the min, mean, and standard deviations? How are they changing week in, week out? Once again, for our numerical columns, we can calculate those drift metrics such as Kullback-Leibler, Jensen-Shannon, Population Stability Index. And we can see here in the light blue we have our baseline, which was calculated on the 3rd, and then every week we're making a batch prediction, and we can kind of see how some of those metrics are drifting from the previous week, if they've drifted at all. And not only just numerical columns, but if you have categorical features as well, you can do things like G-squared drift and see how a categorical column is moving from its baseline week in, week out.